Aditya Patil. I work as a robotics engineer at Peppermint Robotics. It's been a great ROSCON so far and will be. We have agentic AIs, we have talked about agentic AIs, we have talked about physical AI, manipulators, but let's step back a little bit and talk about a very crucial and important system in mobile robotics, in mobile robots, which is Lidar odometry. So first, before we get directly to a Lidar odometry, let's brush up ourselves and try to understand what is exactly odometry. So odometry is a system which helps your robot to figure out how much it has moved in the environment. This is completely different from a system which helps your robot to understand where it is in the environment, which is handled by a localization entity. So in a nutshell, odometry helps your robot to get the position and the orientation of the robot from its initial state using all the sensors available in the robot, be it IMU, be it LiDAR, be it encoders, if you're using a differential drive robot. And from a algorithmic perspective, if we try to understand how odometry works is at every iteration of your sensor, or if you're running it in a while loop, you try to figure out how much the robot has moved from the initial state. You accumulate this information and then you provide this to all the subsequent systems into the in your robot. Now you may wonder, why do we really need odometry? Like, what is the need of odometry? Well, odometry is essential in two aspects. First, localization, which is the second part. Like, odometry helps your robot to understand how much the robot has moved, and localization helps your robot to figure out where the robot is in the given environment, which could be a 2D map itself. Now, the way localization works is, for example, let's take AMCL, Adaptive Monte Carlo Localization. The way localization works is it needs to know how much the robot has moved to figure out heuristically where the robot is in the environment. So for every algorithm, every localization algorithm that works needs to know how much the robot has moved. And this information is provided by the localization, the odometry system in your robot. Then we have navigation system. So navigation in an autonomy stack, navigation helps your robot to go from one position to the next position. And if we divide this navigation system, like, the navigation system is broadly categorized into two sections. The first is the planner, which helps your robot, which gives your robot the actual path to go from the current location to the next location. And then we have controllers. Controllers help your robot to agnostically follow this path. And to follow the path correctly, the robot should know where it is in the environment, which boils down to the localization problem, and the localization problem again needs odometry. So the odometry forms your very basic building block of your robot being of an autonomy stack. Then how do you, before we get to Lidar odometry, there are a few things that we should know about. First is, how do you even generate odometry? There are two things. There are multiple ways you can generate odometry. The first is, you can have, the most common way is an encoder-based odometry. So if we have a differential drive robot, what we tend to do is we attach encoders to the motors, and mathematically we figure out how much the wheel has rotated, and by that we perform an inverse kinematics over it and figure out how much the robot has moved. And then we have Lidar odometry. So how does Lidar odometry work in a nutshell? It's just figuring out how much the robot has moved using just LiDARs. Now, one question arises very frequently is it really necessary to use Lidar odometry in our robots? Like, if the encoders work really well, is it really necessary to use LiDARs in the first place? Well, there are a couple of scenarios where encoder-based odometry tends to fail, and Lidar-based odometry has a better advantage on conventional encoder-based odometry. The first is the principle, the way the both system works are, encoder-based odometry relies on pure rolling motion. So if there is any chance the robot is operating on a rough terrain, the encoder-based odometry going to fail. The same thing, the dependencies. If your robot is not in a good contact with the ground, your encoders are going to give a bad result, they're going to give a noisy result, and they're going to fail. It's the same thing. The basis is essentially the same. If we are, like let's take an example of a differential drive robot compared to a tricycle model enabled robot. So in tricycle models, your drive wheel is at the front and your steering wheel is also at the same position. And in those cases, there is high chance your wheel might slip. So in cases where your wheel slip, you tend to get a very noisy and a very incorrect odometry. So LiDAR odometry helps you in those scenarios. So how do you generate LiDAR odometry? Like there are a couple of algorithms which help you generate LiDAR odometry. The first is ICP, iterative closest point. That's the basis of the algorithm. So if we talk about ICP, what does ICP do? So since ICP has to work on LiDAR, the ICP needs two consecutive point clouds. And the main objective of this algorithm is to get a transformation from the previous scan to the next scan, so that if I transform the former point cloud and if I impose them together onto each other, they fairly seems to be similar. Then we have NDT, normal distribution transforms. Instead of representing each point cloud as an XY coordinate, what we do is we represent them as a Gaussian distribution. So instead of discretizing your point cloud, you end up representing them in a Gaussian form. And then we have feature-based matching. So feature-based matching is a process where instead of using raw point clouds, what we do is we extract few features from that point cloud. It could be either a plane, maybe a circle, or maybe a square. Now what is KissICP? So KissICP is an open source package developed by Photogrammetry and robotics lab at University of Bonn, Germany. And this algorithm, this open source package is very interesting, and it just works out of the box. Like the proposal that they have is this LiDAR odometry pipeline just works without making any changes. And it stands for Keep It Simple and Sweet ICP. So how does this algorithm even actually use your point cloud to generate odometry? Well, it is consolidated, it is distributed into multiple steps. So first step is essentially to pre-process your scan. Since a point cloud generated by LiDAR is memory heavy, like we can assume it consumes a lot of memory, we have to pre-process it. Now, what do we do in a pre-process step? The one thing that we do is de-skewing. So if we consider rotational LiDAR moving on a robot running at 2 meters per second, then the first point at the rotational section and the last point at the rotational section can represent a different position if the LiDAR is moving. So we have to first pre-process the LiDAR and fairly make it an ideal one. Then we perform a two-step voxelization process. So voxelization is downsampling the point cloud into less number of points where you ensure you do not remove all the necessary features, as well as you keep the size of your point cloud as high as possible. And next is, once we downsample the voxel, we create a local map. And we use this local map to perform ICP with the current scan and the local map. And then we have model updation. So when we are performing ICP, iterative closest point between the local map and the current scan, we find correspondences. So correspondences performing a one-to-one matching between each consecutive point in the local map and the scan. So the correspondences, when they are formed, the way we find correspondences is we pick a particular point in the local map, we get another point in the PCL, and we find the distance between them. If the distance is less than a threshold, we say this is a good correspondence and we consider these two as a single pair. And if our estimation of the odometry is getting slightly off from the model that we have, we update the model using the error between our estimation and correct value being generated by the odometry. From an programmatics perspective is as simple as this. You get your PCL in a function. Let's say this is a register function. You get your PCL in the form of eigenvector, which is a vector of eigenelements of vector 3D, which represents a point. Then you pre-process it. You can either deskew it, or you can choose to not deskew it. Then you voxelize it based upon how compute you have and how much you are willing to release the features in the environment. Then you have adaptive thresholding. So adaptive thresholding performs the how intricately I want to perform the correspondences. Once I have adapted the threshold, I perform an initial guess how much the robot would have moved. Then actually I perform the ICP matching, and once I get a new pose, I compare the current pose and the initial guess using pose difference. And once I get the model deviation, I update the model, I store the current local scan in the current PCL in the local map, and then I repeat this process again and again. But is it that simple? Like, we know the theory, how it works, it just works. But how do you even get it working? Is it as simple as you clone the package, you build it, you remap few topics, and does it work? Does it start working out of the box? There are few tricks and tips which help us do that. And the first is the parameters. Every odometry and ladder odometry algorithm has few parameters which needs to be configured based upon your application. So if you're running your robot in an outdoor environment, you need a separate set of parameters. If you're running your robot in an indoor environment, you need a different set of parameters. It also depends on which LiDAR are you using. If you're using a RoboSense, you need a different set of parameters. If you're using a Velodyne, you need a different set of parameters. The first set of parameters are actually data. So it represents how your data is. If you have a very bad LiDAR, which is not a case nowadays, you tend to deskew it. But you should take care, you should not deskew a good scan, because if you try to deskew a good scan, you will end up again skewing it. So skewing is the first step. Second is setting your max and min-max range. So there are scenarios where you really don't want to incorporate a very far information into your local map. So in those cases, what you do is you crop your scan, and there are cases where your robot might end up detecting few parts of your robot, which also can reduce the quality of the local map being generated and being stored. So these parameters help you restrict your point cloud of your interest. Then we have mapping, where we define how well we want to define the local map. The first is the voxel size, and the second is the max points per voxel size. So voxel, when we are performing a two-step voxelization, we have the feasibility to define what should be the size of each voxel. And we also, when we are creating the local map, we have the privilege to represent multiple points as single voxel. So max points per voxel help you do that. Then we have thresholding parameters. So the initial threshold defines what will be your initial guess. So if I set it to a, say, value 0.5, then it assumes that whenever I'm performing correspondence, I should not choose points greater than distance of 0.5 meters. And min motion model threshold, which defines if the if the estimation of the odometry is getting very bad, then what is the threshold when I say it is very bad? So this parameters defines that the threshold of being very bad. And then we have registration. So max number of iterations define how much the ICP algorithm keep iterating to get the maximum out of, to get the correct transformation of the local map and the PCL. And we have convergence criteria and max number of threads. So convergence criteria define how good you want to find the transformation. So if you keep your convergence criteria very high, then you won't be getting good results. So you tend to keep your convergence criteria very low, but you should also ensure that you do not keep it very low, that you end up consuming a lot of CPU, because this is you have to get a fairly balance between getting very good results compared to very consuming a lot of CPU. So there's a balance that you have to maintain, and the max number of threads define how much thread your algorithm, your module is going to consume. And that's it. That's KissICP. That's how you get a lidar odometry working on a mobile robot. And thank you. Thank you.